The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Well, we're back, and today we will consider solutions to harmonic oscillators with damping, damped harmonic oscillators. And what I thought would be best, in order to focus on the new part, the question of damping, what effect it has on the motion of harmonic oscillators, I decided I'll take an oscillator, which is one of those we considered last time. I could have taken any one of them, and added to it a drag force. So let me discuss what we're going to consider. Suppose we have a rod, a uniform rod of mass m, suspended from a pivot here. This is the vertical plane. So this rod, imagine a ruler, for example, with a nail through the end of it, can oscillate in the plane of this board. So we're again considering rotations in two dimensions. Okay? We will consider rotations which are anti-clockwise, like this, to have a positive sign, and if it's clockwise, that's a negative rotation. This particular mass rod, we assume, has a mass m, it's uniform, length L. And initially, it's just suspended like this, so at time equals 0, this is the position, and at that instant, we hit the bottom. There's an impulse acting on it, and that impulse instantaneously gives an angular velocity to this rod, which is, of course, the rate of change of the angle, and we assume it has some number, all right? And so that it's easy for you to remember what that number is, I'm calling it the angular velocity at t equals 0. But remember, this is simply the initial angular velocity that this rod has. At any instant of time later, this rod will be at some other angle. It's shown here, theta of t. This is at time t. And it may be moving at that time, and the angular velocity in this direction we call theta dot t. These are anti-clockwise rotations, and so these are if they're positive, this is at that angle, and if this is a positive number, this is rotating in that direction. So this is the same simple harmonic oscillator we considered last time. And what I now want to take a slightly more realistic situation. All harmonic oscillators in the universe have some drag, maybe very small, some loss mechanism by which they lose kinetic energy. So we're going to assume that this oscillator has some drag torque applied to it. Could be friction around the pivot, it could be the air, this could be inside the liquid, you name it. Now, I am going to make the assumption that the presence of the damping mechanism exerts a drag torque on this rod, and I'm going to make the assumption that the drag force is proportional to the angular velocity. Since the drag force is in the opposite direction to the angular velocity, obviously, there is a minus sign here, and this is the constant of proportionality. Now, you may well ask, why did I assume this is the case? Is that because in nature it's normally like that? No. The reason why I chose this form is very simple. I know from experience that if I use this drag force, I can analytically solve my equations. If I take a more realistic version of the force, then the final solutions I'm going to get are not analytically soluble. It doesn't mean you can't solve them. You can solve them by a computer, but for teaching you how to solve problems is not going to be very helpful if I then say go into a computer and get the computer to solve it for you. So the choice of this, a resistive force which is proportional to the rate of change of position of the rod, is chosen for that reason. The other thing I will once again, because of what we saw last time that happened, assume that the displacement of this rod is small. We're only going to consider small oscillations. In other words, we will only assume this angle to be we'll assume it's sufficiently small so that we can approximate sine of the angle by the angle itself. Again, the reason why we do that is so that at the end we'll be able to solve the equations of motion. Now, if you ask yourself, hold on, we're doing all these approximations, does this correspond to reality? And the answer is the following. In problems that we are doing on the board like this, we are taking idealized situations. For those idealized situations, the prediction of what will happen is exact. But since the description of the situation is not exactly equal to what you'd normally have in the world, the answers that we get are only as accurate as our assumptions, to the degree of the assumptions. But they certainly, from solutions like this, we can get a sense, an understanding what happens. Because making, for example, the drag force slightly different will not qualitatively change what the actual motion is, etc. And this happens throughout so-called problem-solving land in any physics that you consider. Okay, so this is the physical description of the situation. And what we want to do, as before, find out what this rod will do qualitatively as a function of time, and also be able to predict exactly where it will be at a given instant of time. All right? So that's what I mean by I'm going to solve this problem. Now, I chose the same oscillator, as I say, so that you don't have to focus so much on deriving the equation of motion, but more on what the frictional force or frictional torque does, how that changes what we learned before. So, here is the free body diagram or the force diagram which corresponds to this. We have, here is the pivot, this represents the rod. What forces act on this rod? Well, there's going to be the force of gravity, and you know from the studies of rigid body motion that we can understand what torque this force exerts by considering that the force of gravity acts at the center of mass of this rod. So if you take the center of mass, this location, then there will be a force of gravity on this mass, the mass of the rod M, so there will be an mg force acting downwards there. This force applied to this rigid body will exert a torque. In this case, it will be a clockwise, a negative torque. All right. In addition to that, there will be a torque acting on this due to the frictional force, and that we said will be we said we will call b theta dot. All right. So, what is the equation of motion for this rod? The acceleration of the angular acceleration of this rod from tau is equal to I alpha, the acceleration will be equal to the torque divided by the moment of inertia. Since this is rotations of a rigid body in a plane, in 2 dimensions, I don't have to write any vector quantities. These are I'm writing the equations. This is the component of the rotation about an axis perpendicular to the board here. All right, so the angular acceleration will be equal to the total torque, which is the torque due to gravity plus the torque due to the drag, divided by the moment of inertia. And by the way, the moment of inertia of a rod like this about one end is 1/3 ml squared. Okay, so this is equal to, this is the torque due to gravity on this. It's minus, because as I've mentioned here, it's a clockwise torque, minus b theta dot, that's also minus there, because the drag force is always in opposition to the angular velocity, all right, divided by I. As we did last time for the harmonic oscillator, in order for me to write fewer numbers or algebraic symbols on the board, I define some quantities. I will define omega 0 squared to be equal to 3g over L. I'll define gamma to be b over I, that constant proportionality divided by the inertia of the system, the moment of inertia. And I will, as I said, assume that this angle is always sufficiently small that for the accuracy with which I want to predict what will happen, I can assume that sine theta t is equal to theta t. Now, let me be honest with you. I define these quantities not only to make my life easier in writing things down, but as you will see as we go on, it will serve a useful purpose for comparing how all sorts of harmonic oscillators behave with or without damping, etc. Okay, if I take these definitions and make this assumption, and I take this and play around with the algebra, I will end up with this equation. I end up with an equation that the theta double dot, the second derivative of theta, the angular acceleration plus gamma times the angular velocity plus omega 0 squared times the angular position is equal to 0. This is the equation of motion for this system. And the other thing which we know, that initially the theta at 0 is 0, and the initial angular velocity is this number, angular velocity at t equals 0. These three equations are absolutely, from the point of view of physics, equivalent to the description we had. Here we had this physical description of some bodies, this rod, etc. This is a mathematical, these mathematical equations describe this situation. In order to predict what will happen, what we now have to do is solve these equations. Okay? So that's what I will do now. So I will solve this equation. And let me remind you, as I discussed in the past, but I cannot emphasize it enough now, I am not trying to teach you mathematics. I am trying to help you learn how to solve physical systems, how to predict how a given physical system will behave as a function of time. So I will make, for me, mathematics is a tool. I need a solution of that equation. And this is a linear second-order differential equation in time. And I know from mathematics that if I find a solution of this equation, which, well, by definition, if I find an equation which solves that, and if it has two arbitrary constants, in other words, the solution satisfies that equation for all values of those arbitrary constants, then I have found the one and only solution of that equation. All right? And so, let me tell you, I will solve this by using this uniqueness theorem. I know that that equation, unfortunately, is a little harder to solve than the one we did last time for simple harmonic motion. One finds that the solution of that equation actually depends on the type of solution you have, depends on these constants. For the harmonic oscillator, it did not. The type of equation which was the solution did not depend on those constants. Here it does. One finds that if you have gamma squared greater than 4 omega squared, or omega 0 squared, in other words, if you have this B constant bigger than a certain amount, this means you have heavy damping. You have one kind of a solution, while if it's the other way about, if this is bigger than that, you get a different kind of a solution. It's not obvious, but that's what mathematics tells you. So let me consider first the case of strong damping. B is big, all right? So we're talking about situation, you have this oscillator, but there's lots of friction, and so it doesn't move smoothly at all. This is greater than that. Under those conditions, you find that this equation satisfies our equation of motion. Now, actually, Professor Walter Lewin, in his lectures, did show you how you can prove that this equation satisfies our equation of motion for these specific conditions. He used complex amplitudes, and you can review his lectures and you can see it there. Or you can look it up in books on the solution of differential equations. For me, it is adequate that I found a solution which satisfies this equation. Now, note this is a solution of that equation where the alpha 1 and alpha 2 are defined here. It's all defined in known quantities. Gamma, omega 0 are known quantities for any specific problem, in particular for the one we are solving. All right? So here, every term is known. The A and the B are the two arbitrary constants. In other words, this equation satisfies our equation of motion for all values of A and B. So, again, by the uniqueness theorem, this is the most general solution to our problem, provided the damping is very high. Okay, if this is theta of t, then of course the angular velocity theta dot of t, just differentiate here, and I get minus alpha 1a e to the minus alpha 1t, and minus alpha 2 b to the minus alpha t. We want to find the solution to our particular problem. So we found it that satisfies the equation of motion for our system. We now want to make sure that we have a solution which satisfies the boundary conditions. In other words, which is consistent with what we said this rod was doing at t equals 0. At t equals 0, we said the rod was vertically, so theta of 0 is 0. And we also said that at that instant there was an impulse given to the rod, and so its angular velocity at t equals 0 was this number, the angular velocity at t equals 0. All right, so we must now make sure that the a and b, these arbitrary constants, are consistent with these initial conditions. And obviously how you do that, you take this equation, and I take what is theta at t equals 0. Well, it's 0, so that's 0, equals to when t equals 0, this is 1, so it's a, plus when t equals 0, this is b, so it's a plus b. So we know that a must be equal to minus b. That's to satisfy the boundary condition that the rod was vertical at t equals 0. How about the other boundary condition? We know that at t equals 0, the angular velocity, theta dot, is angular velocity at t equals 0. Okay? And so, angular velocity at t equals 0 must be equal to minus alpha 1 times a, and t equals 0, this is 1. So it's minus alpha 1a, and here minus alpha 2b. Okay, we now have two equations, right, with two unknowns, two algebraic equations. Therefore, we can find a and b. In fact, we found already that a is equal to minus b from this equation. And then replacing b by minus a, we find that a is angular velocity t equals 0 and alpha t minus over 1. So what do we find? We have found that the specific solution to our equation of motion, which satisfies these boundary conditions, is theta of t, all right, is equal a e to the minus alpha 1t. A is angular velocity at t equals 0, right, into e to the minus alpha 1t, right? And b is minus a, so it's minus e to the minus alpha 2t. Okay? So, we have solved our problem. This equation describes the motion of this pendulum, this compound pendulum, the rod, completely. If I tell you that, if you ask me for a time, I will tell you exactly the angle at which this will be hanging. There are no more unknowns in this. Furthermore, it gives me a sense of what that rod is doing. And actually, it's a bit of a surprise. We've considering here an oscillator, we'd expect an oscillator to oscillate. This equation doesn't oscillate. It is the sum of two exponential functions. If I just qualitatively plot this, okay, if I plot it, just qualitatively, alpha 2, if you look, compare alpha 2 to alpha 1, you find that alpha 2 is greater than alpha 1. Okay? So this exponential has a bigger exponent. It will be dropping faster than this one. So what do we have? I have some, this is my angular velocity at t equals 0. Okay. Let's consider one of them. This is 1. It's an exponential function. Here I'm plotting the angle as a function of time. I'll get some exponential function. Okay, like this. Starting at that value. And the other function is also an exponential one, which has a higher value of the exponent, and therefore it will drop more quickly, starts with the same amplitude, so it will go more quickly like this. Okay? The net motion is the sum of, is the difference between those two. Take this one minus that one. Okay? What does that look like? Well, qualitatively, you can see I'd start at 0. Right? Okay? Far out here, it'll be 0, because the two exponentials will approach 0. So out here, it'll be 0, or approaching 0. Okay? It'll be some magnitude in here. And so I will get something like this happening. Okay? It's the difference of the two exponential functions. Isn't it amazing? Let's think for a second what we have shown. We've taken this harmonic oscillator, we've put it in a situation with a lot of friction, we gave it a kick, all right, and we described it in terms of these mathematical equations. I then blindly applied mathematics, solved these equations, and predicted that this will be the motion. No oscillations. Let's stop now for a second. By common sense, what would you expect? Imagine you had this rod in something which is very, very viscous, very high drag. You give it a kick, it'll move. Because of inertia, it will move, but it'll get slowed down. It'll finally come to a halt, and it will slowly come back. But if it's so, the resistive force torque is so big, it will never overshoot. So this is exactly what you'd expect. And as I say, it is amazing. I've always found it amazing, because this is a magnificent example that mathematics is the language that one can use to describe nature, and that solving the mathematical equations predicts what will actually happen in a given situation. All right. Enough of philosophizing. Let's now consider the other possibility. So I'll now do a second problem where I will have very weak damping. So imagine a more realistic situation. We take our pendulum, this compound pendulum, and we include the resistive torque due to the air, for example, that's there, etc. Again, I am taking the same pendulum so that we just focus on the effect of the damping. Okay? So, I think I have it here. Everything up to here will be exactly the same. The only thing we've now changed, we've said that this little b is big, such that the gamma squared is much smaller than 4, is smaller, it doesn't have to be much smaller, so that gamma squared is less than 4 omega squared, and in other words, b is less than this. So it's the weak damping case. You may well ask, hold on, why look for any other solutions? I have found a solution for this equation before, and up there was the 2 exponentials. Why can't we just take those and say, look, that equation satisfies this equation, that value of theta t, and just repeat this? Well, try it, and you'll see you immediately get into difficulties. In this formulation, you see that alpha 1 and alpha 2 include a square root of gamma squared minus 4 omega squared. We had no problem with that when gamma squared was greater than 4 omega squared. You can take a square root of it. But if gamma squared is less than 4 omega squared, that square root is square root of a minus number. And how is that going to represent a physical situation? So the method breaks down. In other words, for this case, we have not found an equation which satisfies our equation of motion with these boundary conditions. So we've got to try again. And there is an equation that does. And I've written it here. Okay? One finds that theta of t is equal to some arbitrary constant a, e to the minus gamma over 2t times cosine omega prime t plus phi, where omega prime is well defined in terms of omega 0 and gammas given here. And there's no problem. We have now gamma squared is less than that, so this is a real number, so there's no problem with that square root. Okay, plus phi, so we have 2 arbitrary constants. Try it. Take this equation, differentiate it twice, and calculate it. Then differentiate it once and multiply it by gamma. Don't differentiate. Take that equation and multiply by omega 0 squared. Add those 3 terms, you'll get 0. I tried it last night to make sure I didn't write the wrong thing here. Okay? So that really works. Again, if you want to know how did I find this equation, did I take it out of a hat like a rabbit out of a hat? No. You can look it up in books, solutions of equations, or actually, Professor Walter Lewin did derive this solution also using complex amplitudes, and you can find it in his lectures. But from my point of view, I don't care where I got it from. That works. Okay? So this must describe the motion, and it has 2 arbitrary constants, which I can find because I know the initial conditions for this pendulum. So once again, now I will try to find the 2 arbitrary constants. Okay? How did we do it before? By taking our solution. Well, we know that theta of 0 is 0, right? Therefore, if 0 is equal to a e to the minus gamma over 2t, that's t is 0, so that's 1, cosine, t is 0, so I get phi. Okay, so one boundary condition tells me that phi is pi over 2, or there are others, minus pi over 2 works, etc. Doesn't matter, take any one of them, and provided you're consistent, the other one will make up for it to give you the same answer. All right, so anything that satisfies this boundary condition is fine for one of those constants. All right, now the other one tells me something about the initial angular velocity of the rod. So I need to calculate the angular velocity of this rod. So here I calculate theta dot t at time t by differentiating theta, and I get this lower equation. And now again, theta dot at 0 time is equal to, we know it is, this number, angular velocity at t equals 0. So in this equation, I plug that in. I get that the angular velocity at t equals 0 will have to equal to a, okay, e to the minus gamma over 2t, t is 0, so that's 1, into minus omega prime, okay, sine of omega prime t, but t is 0, so that's 0. Phi is that, so sine of pi over 2, because we found phi, that's 1. Okay, so I don't do anything with that. So, all right, minus gamma over 2 cosine of omega prime t, t is 0, so it's cosine of phi. Phi is pi over 2, so that is 0. So that's all all right? Therefore, A is equal to, now, angular velocity at t equals 0, right, divided by omega prime. Okay? And therefore now, all right, let me move over here. So now I can write the full solution. I have found everything, and I find that theta of t from the second line down is equal to a, which we found, angular velocity t equals 0 over omega prime. All right, minus, there's a minus, but you'll see, and now it's cosine omega prime t plus 90 degrees. So that's the same as minus sine of omega prime t. The two minuses cancelled, so I get a plus. Okay, and if by the earlier on you chose, for example, here minus pi over 2, then both of those signs would have been plus, and you still get the same answer. So it doesn't matter. The algebra looks after itself. Okay, so we have found the solution of this equation, to an equation of motion, with these boundary conditions for the situation where the gamma and the omega 0 squared are such that they correspond to the low damping situation. What kind of a motion is that? if I plot this, now again, as we did as a function of time, what, if I had a room full of students here who would correct me, then I would have caught the mistake. If you look at the second equation, it says theta of t is a e to the minus gamma 2t cosine omega prime t. When I rewrote it, plugging in the value of a, I forgot the e to the minus gamma over 2t. Okay? Sorry about that, and we continue. So now if I plot this, what do I see? If it wasn't for the e to the minus gamma over 2t, it would be a sine. All right? That's what it would look like. T, and this is the angle theta of t. Okay? This would be the simple harmonic motion with no drag, no damping. But this function is multiplied by an exponential like this, which is dropping. So the net result, and excuse my sloppy drawing, is this modulated by that. So it'll be something like, you know, like this. Okay? So what we get is damped harmonic oscillation. Okay? Now, again, I can't resist sort of pointing out, to me it seems almost miraculous. You have the same equation in form with the same boundary conditions, predicting completely different behavior if some of these constants are bigger than the others or vice versa. So the mathematics has it built in that kind of solution, those two kinds of solutions exist. And that corresponds exactly what you would expect if you imagine an oscillator with damping. If you have this oscillator, which is, if it's highly damped, as I said before, you'd expect this crazy motion to go slow, reaching a maximum, slowly coming down and coming to a grinding halt. Or if it's lightly damped, you would expect this to almost behave like a normal harmonic oscillator, but with slowly losing energy to the damping and oscillating with smaller and smaller amplitude, which is exactly what the mathematics said would happen. Okay. I always like to ask a crazy question: how does the oscillator know what the mathematical solution is? But somehow or other it does. Okay, it's a crazy way to phrase it, but I always think of that. Okay, so let's put together actually what we have seen in a combination of last time and this time, my problem solving, my attempts to teach you how to solve problems. What we found last time was that we took three different harmonic oscillators. One was a mass on a spring. Another was this rod oscillating like this. The third was an electrical system, an LC circuit. In each case, we found that we could, the equation of motion looked exactly the same. The only difference was what the variable, what was the name of the variable. For example, in the case of the spring, we called the displacement from the equilibrium was a distance. So this equation was of this form, where the psi was a y. All right? When we came to this oscillating rod, the variable was, the quantity which was displaced from equilibrium was an angle. So this psi was a theta. In the case of the LC circuit, the quantity was a charge. So it was the charge which was displaced from equilibrium. But I could have summarized the equations of motion for the 3 harmonic oscillators by this one equation, and just tell you, well, this is the equation of motion for that, and put in the appropriate quantity which is displaced, and also put in the appropriate value of this constant, which for the spring was k over m, for the rod 3g over 2l, for the LC circuit was 1 over LC. And believe me, we could have taken 1,000,000 harmonic oscillators with no damping, any one you can think of, and I could reduce it to this form. So here is something new that we observe, that you can take lots of physical situations, but describe them in terms of the same mathematical equations. The same mathematical equation can describe millions and millions of different kinds of harmonic oscillators. So that is another feature of the scientific method which is very important. It means now we don't have to understand in every little thing that happens in the universe. We can reduce it to a smaller subset of descriptions. Okay, now we've now added a new feature today. We added some loss mechanism. We took a specific kind where the resistive force or the resistive torque is proportional to the velocity, or the analogous of, if it's for, in our case, to the angular velocity of the rod. And we derived an equation of motion which looks like this, where these psi's for the oscillator we considered was the angular displacement. I don't have to be an Einstein to, by analogy to what I said here, to say, look, I could have taken any one of the oscillators in the universe, and this with damping, if the damping is proportional to the velocity or the analogous quantity of velocity, I'll end up with this equation of motion. So this is the equation of motion of simple harmonic motion. This is the equation of motion of damped harmonic oscillators, every one of them. And if you, but there is an interesting difference we saw today. There is only qualitatively one kind of solution here. In the case of the damped harmonic oscillator, there are two qualitatively different solutions to that. One is the sum of exponentials, and the other is damped harmonic motion. Both the quality of the solution and the details, whether is oscillating fast or slow, etc., depends on those quantities, the gamma and the omega 0 squared, which in turn, for example, in the various cases, it's k over m, 3g, etc. So that will describe all oscillators, and in any particular oscillator, if you want to know what exactly happens at a given instant of time, you then need also to know those two constants, the boundary condition. If I have some mass on a spring oscillating, where it will be at some later time does depend where it is at this very instant. Okay. Finally, there's just one more thing I would like to do today, and it's the following. Oscillators are not only nice in order to give you a lecture on oscillators or to show you how to solve them, they are practical devices. So sometimes we want to know some property of a given oscillator. Well, there are two properties which are describe the quality and what of a given oscillator and what its behavior is. One, you've seen already, is to do the period or the frequency of the oscillator. In other words, you could have one oscillator which goes very slowly. You can have one which goes very fast. If you want to describe, I have an oscillator, you want to tell somebody what it's like, a crucial number is what its period is. No, 1 over the period, which is the frequency. Imagine, for example, a bell. That's an oscillator. You could have a bell which has a low tone, or a very small one with a very high-pitched tone. So that's one number that's important. But there is another number that's important, whether it's a good or a bad oscillator. Right? And it's obvious what is a good oscillator. A good oscillator is one that oscillates for a long time. A bad one is that doesn't oscillate very far, with a high frequency, which doesn't continue oscillating for a very long time. But again, you would, I'm sure, agree with me that it isn't just how many oscillations it does, say, in a given time, like 1 second. If I take an oscillator that makes 1 oscillation per second, okay, then if it survives 1 second, you wouldn't say it's a very good oscillator. It barely made 1 turn, okay? While if the oscillator is making 1,000,000 oscillations per second, and that survives for a second, you would say that's a pretty good oscillator. It made 1,000,000 oscillations before it ran out of steam. Okay? So to quantify the quality of an oscillator, we use a term, and being very imaginative, we call it the quality of the oscillator, or Q value. So I will finally want to derive for you, for this particular oscillator, what is its Q, or Q value. And that's the last thing I will do today. Now, it only makes sense to talk about the Q of an oscillator if it's at least a reasonably good oscillator. This one, this overdamped one, who didn't even make 1 complete cycle, doesn't make sense to talk about its Q. So the only case where it makes sense to talk about the Q of an oscillator is if it makes at least a few oscillations. All right? It's got to be the underdamped case. So I will now calculate for you what is the Q of this compound pendulum, this rod, which oscillates under conditions where the drag force is small, so that it has this undamped motion. Okay. So let me do that. The Q value of an oscillator is defined by, no good reason, pi multiplied by, okay, the number of oscillations the oscillator makes before its amplitude drops by 1 over E. It's a formal definition. Okay? So take some oscillator, which is a good oscillator, so it oscillates like this. It's decaying. This has an exponential form, as we saw, for a damped harmonic oscillator. All right? And we ask the question, how many oscillations it makes before the amplitude drops by 1 over E. Okay? So, and for historic reason, one takes pi, multiply by the number of oscillations for amplitude to go down by amplitude over E, 1 over E. Okay? Because the energy stored in an oscillator is proportional to the amplitude squared, this is equivalent to 2 pi times the number of oscillations it takes for the energy to go, to the energy over E. These are equivalent because one is the square of the other. And in fact, just let me tell you, I'm digressing here. Originally, this was the definition. The 2 pi is there because in the definition, one said what will be the change of phase of the oscillator for the energy stored in the oscillator to go down by 1 over E. If you're talking about the change of phase rather than number of oscillations, you have a 2 pi there because the phase in one oscillation, the phase changes by 2 pi. So historically, this came in, that's equivalent to this, all right? And so we have to calculate that. Okay, now, for this particular oscillator, we actually calculated the motion, how the angle changes with time. And we see that the amplitude drops like e to the minus gamma over 2, right? So we saw that the amplitude drop like e to the minus gamma over 2t. Okay? So, in what time will the amplitude drop by 1 over e? That time will be equal when gamma t over 2 is equal to 1. Right? Then this will be, so you get e to the minus 1. So it will be in a time t equal to 2 over gamma. Okay? Now, what we are interested in is how many oscillations will, in this time, the oscillator make. Okay? But you know the period t, okay, is equal to 2 pi over omega prime, because I'm using here omega prime because that is the angular frequency of the damped oscillator. It was not omega 0 like the undamped one, and an omega prime I defined for you earlier. Okay? But you know that if the damping is weak, omega prime is essentially equal to omega 0. Q is a quality thing. We don't need it exactly. So it's just to give you a feel whether something is a good or a bad oscillator. So since omega prime is essentially equal to omega 0, I'll take the period to be approximately equal to this over omega 0. Okay? So in time t, how many periods will I have? I have to divide t by the period. That'll be the number of oscillations I'll make. Okay? So it's 2 over gamma divided by 2 pi over omega 0. Okay? And so this is the number of oscillations. So the Q will be pi times the number of oscillations for the amplitude to drop by this. Okay? So the Q will be equal to pi times this quantity, all right, which is 2 over gamma divided by 2 pi over omega 0, which is equal to omega 0 over gamma. So the quality of this particular oscillator will be equal to omega 0 over gamma, and I hope I still have it. Do I have that? Where do I leave it? Well, you could, by going back in through this video, omega 0 we defined earlier on, and gamma also, and so you calculated this. Okay, that's as much as I was going to do about damped oscillation for you. Thank you.